So first of all, I would like to thank the organizers for inviting me here so far to the north. So, yeah, I'm going to talk about something different than probability theory. I'm going to talk about holomorphic dynamics, in particular about transcendental dynamics, and about how some procedure, like iterations in the Teichmuller spaces, can be used to obtain certain classification result in transcendental dynamics. So first I give a sort of motivation of my main results from the point of view of holomorphic dynamics. Then I present this main results. It's called classification theorem. Afterwards, I try to motivate it from a little bit different point of view, from the point of view of so-called infinite dimensional Thurston theory. And finally, I just give a very, very rough scheme of the proof of the classification theorem. So let me start. So in holomorphic dynamics, we study simply iterations of holomorphic functions. More precisely, let S be a Riemann surface and F some holomorphic function. Then we simply consider the iterates of F at every point and see what's happening in the long run. So yeah, just my notation here, f to the n always means the iterate, not just the usual degree. Well, in particular, we will be interested in the case when S is either a complex plane or sometimes a Riemann sphere. Then, well, if S is a complex plane, then F can be either a polynomial or a transcendental entire function. And yeah, well, since I'm going to talk about transcendental dynamics, so I'm mostly interested in transcendental entire functions. So, but in both cases, either for polynomial and transcendental function, we can define. Well. Well, holomorphic functions from C to C, which is not a polynomial, like exponential well, exponential is the base, the easiest. Okay. So, in both cases, one can define a sort of very natural dynamical set called escaping set. So, this is simply the set of points Z, which under the iteration of F tend to infinity. So they escape to infinity. Okay? So it is in holomorphic dynamics, it is sort of important, often important not to study just a single function at a time, but rather to consider, to parameterize a family of functions and to study a parameter space of functions, so that a few functions at the same time. One of the most important examples in of such a parameter space is, of course, the famous Mandelbrot set. So here it is depicted in black. So the Mandelbrot set is the set of parameters C in the complex plane, such that the critical point 0, the orbit of the critical point of 0 is bounded under the iterations of the polynomial Z squared plus C. So, yeah. So, well, you know, this is a very like famous set. There are many famous people, famous mathematicians have studied it. Like a few Fields medals were issued by for different works related to this Mandelbrot set. So, of course, it's of interest. And in particular, to understand it better, one wants to understand its boundary. And to understand its boundary, one way to understand better its boundary is to study the complement of the Mandelbrot set. So more precisely, the complement of the Mandelbrot set is a set of parameters C for which critical value of the polynomial z squared plus c escapes or tends to infinity. So in this case, there is it's a theorem from good old days that every quadratic polynomial corresponding to some parameter in the complement of the Mandelbrot set can be characterized by the dynamics of a critical value represented by two parameters, speed of escape and or potential, and combinatorics or external angle. Let me just give a brief comment on this. It's sort of very easy to explain what it means. So assume that I fix some polynomial z squared plus c, and also let some point z naught belong to the escaping set of f, and also denote by zn equal to the nth iterate of z naught. Then there exists a real positive real number r and angle phi belonging from 0 to 2 pi such that Zn over R e to the I phi to the 2 to the n tends to 1. So that it's in a way that the dynamics, the escaping dynamics of this polynomial is in a sense conjugate to the dynamics of simply z squared on the escaping set, so that, well, it's easy to see. Well, it's not easy to see, but it's sort of natural, because when the z is very big, then these are almost two equal polynomials, because c is just some fixed number. And then simply this for r is a speed of escape, and this phi is combinatorics. That's what we mean by this. And here, in particular, you can see that there are some lines in the complement of the Mandelbrot set. So these lines, they tend to infinity. So they correspond to points which have the same combinatorics or the same external angle, but different speed of escape. So the points that are closer to infinity correspond to parameter which escape faster to infinity. Okay, this is a classical picture from old days. Now you can ask a naive question, easy question. Can we do some similar characterization for transcendental entire function? Well, and the answer is the main result of this research. Well, before stating it, I need to tell you a little bit more about which exactly entire functions we consider. So we consider rather some sort of simple families of transcendental entire functions. You see, simple is in quotation marks because it doesn't make the study of them very simple. So the first one is, of course, the exponential family. It's just e to the c plus kappa, where kappa is some parameter. It's analogously is a sort of toy example as for polynomial dynamics when you consider polynomials z squared plus c. and a more general family, which is simply composition of polynomial with the exponential. So for the purposes of this talk, you are welcome to keep in mind just this first one. This is a toy example, but it inherits all many of the key features of this family in our constructions. So then I would like to remind you what is the singular value of the critical, what is the singular value of f. It is, in our case, it is just a union of critical values and asymptotic values of f. And for the case of exponential family, we just have one asymptotic value equal to kappa. So basically, this is sort of branching points where the function is not where the function branches. So in all cases, we have functions of finite type. That means they have finitely many singular values. So in fact, for this family, we don't need this closure. It's from more general definition. Okay, and then I would like to show you a picture which is sort of an analog to that picture of the Mandelbrot set. Where here we have parameter arrays. So here, what is in gray, you can this is an analog of the complement of the Mandelbrot set. So here you also can see some curves. Here there are many curves. They're all lined, and they correspond to parameters kappa, for which the singular value of e to the kappa escapes, and sort of as closer on this ray the parameter is to infinity, as faster escapes the singular values. But and on points on the same parameter ray, they have the same combinatorics. Combinatorics is defined slightly different for the exponential family, but intuitively intuitively this picture should work for you. I can give you more explicit definition later if needed. Okay, so now the main result is this is a classification theorem. So given if we are given some polynomial p and a transcendental entire function, which is composition of polynomials exponential, denoted by f naught. And well, it has m finite singular values, because, well, infinity is also singular values, but we don't consider it. So I always implicitly mean only finite singular values. And also we are given a list of m allowable speeds of escape and combinatorics, each corresponding to a particular singular value of f naught. Then what happens? Then in the parameter space of f naught, there is a unique entire function g, such that each singular value g escapes with a prescribed speed of escape and combinatorics. So, and vice versa. So every function in the parameter space such that all its singular values escape fast is one of the functions constructed as above. So just a few comments. So here say that, so you can see that here we consider the parameter spaces with fast escaping singular values. So in some particular mathematical sense, it's this is almost the only possible way to escape for the points on the family. There are special cases when the points escape slow, but they are in a way negligible. So we don't study them. Also, I have this vague word allowable here, but it's just I'm not hiding anything under it. It just means that not every combination of speed of escape and combinatorics is possible at all in the family, so that we realize any combination which is all sort of allowed by for any point, escaping point, not only by singular value. So it's no way a restriction to the generality. I'm making a little bit more, sort of try to avoid giving too many details in the statement. Okay, and the key to prove this classification theorem is what we call infinite-dimensional Thurston theory. So let me give a few words about classical Thurston theory, which has which is of importance in the dynamics of rational functions. So the classical theorem stated by Thurston, proved by and published by Dwadi and Hubbard in '80s. So it's called Thurston topological characterization of rational functions. So it says that a postcritically finite branched covering F of the two-sphere is Thurston equivalent or combinatorially equivalent to a rational function if and only if there is no Thurston abstraction. So Thurston abstraction is some particular topological object. You don't really need to know for the purposes of this talk what it means. Also here you can see the definition of when G and F are combinatorially equivalent. It's written in such a little bit vague way, but in particular this means that simply we have the following commutative diagram. So this F, S2, S2. This is phi, this is psi, and phi is isotopic to psi relative to the postcritical set. And postcritical set is just a set of all forward images of critical points. So we consider only postcritically finite functions. Okay, so well, and to prove this theorem, the classical idea is that one should define a special map. It is called Thurston sigma map, acting on a specially chosen Teichmuller space, and then the fixed point of this map, if it exists, it corresponds exactly to this function, to the desired function G. To the desired rational function G, which is Thurston equivalent to F. So, but then we can again ask a very childish question. But what happens if this PF contains infinite orbits? Well, can we in this case also define a sigma map? Will it be strictly contracting? Well, this is an important ingredient in the proof of the classical theorem. Does it have a fixed points? Well, the simplest case is when we have just one accumulation point and all orbits are infinite. In this case, we consider the branched covering, which models either a polynomial with all escaping singular critical values, or a finite type transcendental entire functions with escaping singular values. And that's exactly what we want to consider, so we are interested in this case. And then we can do something. More precisely, well, but sort of it's, let me just give a comment. So it's very difficult to solve this problem in the full generality as the classical theorem is solved, because we have many more different covering models. Well, simply because we have a covering of infinite degree with infinite post-singular orbits. So there are too many things are happening. So we would be modest, and we just want to prove the classification theorem. So, and to prove the classification theorem, we just need a branched covering that model transcendental Tar functions of a particular type with the desired behavior of singular values. But again, we do not provide the proof for any arbitrary topological branch covering of this type. Instead of, we constructed, we use from the classification theorem, we had a list of speeds of escape to combinatorics. So using them, we constructed a special quasi-regular branch covering F, which models the desired singular escaping dynamics. And then this defines a special sigma map acting on the Teichmuller space of the complement of this post-singular set. Well, I will tell you just in a moment what is Teichmuller space. I haven't given the definition yet. So, and then the theorem, which is holds the following theorem. So the sigma map has a fixed point corresponding to the transcendental Tar function with singular escaping dynamics, exactly modeled after all these given speeds of escape and combinatorics. So let me, since I haven't given the definition of the Teichmuller space, I still have to do it. So then the Teichmuller space Tf of the Riemann surface C minus Pf is a set of quasi-conformal self-homeomorphism of C, modular composition with a fine map, and isotopy relative to Pf. So, brief comment what is a quasi-conformal map, of course. So that a rough definition which is usually given is that conformal maps are usually map infinitesimal circles into infinitesimal circles, but quasi-conformal maps, more precisely K quasi-conformal maps, infinitesimal circles into infinitesimal ellipses, but these ellipses cannot be too oblong, so their eccentricity cannot be too big. So exactly their eccentricity is their eccentricity is encoded in this parameter, so that if this parameter is big, then the eccentricity can be big, but it is bounded. So the ellipses cannot be too oblong. So it's like generalization of conformal maps, and exactly the one quasi-conformal maps are conformal maps. So well, the only thing you need to do to know about the Teichmuller space is that they can be equipped with a special metric called Teichmuller distance, and with this Teichmuller distance, the Teichmuller space is a complete metric space. So let me almost already move to the conclusion. So after this table, so here in this table you can see. Oh yeah. So and the Teichmuller space, it is in case when Pf is finite, then it is simply it will be C to the Pf minus 3 manifold, analytic manifold. But when Pf is infinite, it will be something like a C to infinity manifold. And this, of course, creates a lot of problems in the proof. So one cannot simply reproduce the proof from the classical theorem. So, well, here is a table of some of them. So in finite-dimensional case, the mapping class group, well, since we work with isotopy class of maps, we need an efficient way to encode the elements of the mapping class groups. And in finite-dimensional case, the mapping class groups are finitely generated. Infinite dimensions are infinitely generated, which creates a lot of obstacles. Well, another key feature of the infinite dimensional Teichmuller spaces is that if if the number of points in Pf is fixed, then we have only one Teichmuller space in the finite dimensional case. But in infinite dimensional case, we have uncountably many different Teichmuller spaces. So, and also, what's happening is that there is no well-developed theory in the infinite dimensional case. So just some special cases are covered. So this again, big obstacles to prove the theorem or to reproduce the classical proof. So how do we prove the classification theorem? So we define a special, using the data from the classification theorem, we recover, we construct the special quasi-regular branch covering which models the desired dynamics. Then we construct a special compact subset that is invariant under sigma. Then we prove that the restriction of CF is strictly contracting. And then basically using argument from Banach fixed point theorem, we prove that there exists a unique fixed point in this compact invariant subset CF. But out of all these 4 items, the most demanding is the construction of exactly the construction of this invariant compact subset. So it's most difficult. So let me come to the conclusion, just a moment. Okay, so well, in our research, we classify all entire transcendental functions of a particular form, composition of polynomial with exponential, for which all singular values escape fast. Then the key to prove this is sort of to prove generalization of or rather an analog of the classical Thurston's characterization theorem, but for a singularly infinite case. And this involves iterations on the infinite dimensional Teichmuller space. Well, because of this infinite dimensionality, we have a lot of challenges which we have to overcome. So basically, the proof goes in quite different ways than the classical theorem. Well, basically, we construct a special subset in the Teichmuller space, inside of which these challenges are easier to deal with. And this is how the problem is solved in this case. And we expect that the techniques, even though we prove everything for a rather special family of transcendental functions, the techniques should be applied in much bigger generality. So in particular, for the functions of finite type and finite order. So thank you.
Okay, thank you for a very interesting talk. We have time for one short question. No?
I have a question. Okay. So actually, I didn't catch your main result. The first theorem.
The classification, yeah.
Yeah. So.
Okay.
Is an analog of this theorem holds for the classical situation when you consider just a polynomial, not a polynomial exponential?
Well, polynomial is a separate case. So the theorem is true exactly for, as I said, it's here is this classical theorem for quadratic polynomials. For quadratic polynomials. For cubic polynomials, so for bigger degree, it's not known. And in principle, one could try to apply this outline that I do, but there are doubts that it will work because escaping set of polynomials is quite different from the escaping set of transcendental entire functions. So the points by transcendental functions escape much faster, and this is very important in the construction.
So let's speak. Let us thank the speaker again. Sorry.